We will now discuss the one symmetry, which is the star of the show as far as relativistic quantum mechanics is concerned, the Lorentz transformation. In particular, the Lorentz transformation in quantum mechanics. Just to remind you, a Lorentz transformation is one in which the invariant interval stays invariant. Now, exactly what is this invariant interval? To see this, we first introduce a new set of coordinates, space-time coordinates. Every event occurs at a particular point in space and at a particular time, and it's both the time and the spatial coordinates which go into describing what an event is. So, what we use are coordinates as follows. We use coordinates which are written with an upstairs index. These are not powers, these are just suffixes. And x3 is z. x0 is actually c times t, but we are going to use units where c is 1. So we have time, then the x coordinate, then the y coordinate, and then the z coordinate. Now, I am going to deviate from Weinberg's notation a bit here. Weinberg uses exactly this, except that for some reason, he insists on writing x0 at the end. So, for him, the order for any vector, 4 vector, would be a1, a2, a3, a0. However, I am more used to the standard one, which is a0, a1, a2, a3. So, I am going to write it in the standard version, at least what I know as a standard version. Now, in a Lorentz transformation, this quantity stays invariant. x0 square minus x1 square minus x2 square minus x3 square. This is the invariant interval between the event which occurs at x0, x1, x2, x3 and the event which occurs at 0, 0, 0, 0. Now, the sense in which this is invariant is any inertial observer observes exactly the same value for this particular quantity. Well, instead of talking about interval between a particular event and the space-time origin, we can also talk about the interval between two neighboring events, and that interval is given by dx0 whole square minus dx1 whole square minus dx2 whole square minus dx3 whole square. This can be the definition of the invariant interval, or this could be the definition of the invariant interval. Weinberg uses this one. Minus dx0 whole square plus dx1 square plus dx2 square plus dx3 square, which can be written in a compact form as dx nu eta mu nu, where eta mu nu is the diagonal matrix and the diagonal terms are defined as eta 1 1 eta 2 2 and eta 3 3 are all equal to plus 1 and eta 0 0 equals minus 1. So this is a particular way of writing the Minkowski metric, which most of you should be familiar with. A word of warning here. Usually there are two distinct conventions as far as writing this particular metric is concerned. One of them is this one, where the spatial diagonal elements are plus 1 and the temporal diagonal element, the eta 0 0 element, is minus 1. The other one, which is often used, is the one in which eta 0 0 is plus 1 and eta 1 1, eta 2 2, eta 3 3 are each equal to minus 1. Of course, if you were to use one convention rather than the other, your invariant interval will pick up an extra minus sign. But if something is an invariant, the same for all inertial observers, then its negative, of course, is also invariant. So there is no contradiction there. You just have to choose one of the two. Now the reason why I am issuing this warning, despite the fact that both of these conventions for the metric are quite popular and both are used, is the following. It so happens that almost universally people who work in gravitation use the particular metric that Weinberg is using here. That is, the metric in which spatial components dominate or have a plus sign. Whereas, for high energy physics, is typically the energy term which is dominant or the temporal term which is dominant. And in high energy physics, almost universally, the convention is to use eta 0, 0 equals plus 1 and eta 1, 1, eta 2, 2, eta 3, 3 equals minus 1. So, in a way, this is slightly surprising that Weinberg uses what is a general relativist favorite version of the metric in a textbook which talks about quantum field theory and relativistic quantum mechanics in particular. This is slightly unusual, although not unheard of. The one place where I am going to definitely deviate from Weinberg, as I said, is in the ordering. Weinberg puts the 0th index at the end, which has some advantages, but that's sort of unusual, and so I'm going to use the standard one where 0th index comes at the beginning. Now, having said that, the invariance of the interval essentially means that we have this relation eta mu nu dx mu dx nu, which by the way simply means eta 0 0 dx 0 times dx 0 plus eta 0 1 dx 0 times dx 1 and so on, and you can easily check that that exactly means this interval that we have written down up here. This quantity should be the same for all inertial observers. So if the coordinates as measured by another inertial observer happens to be dx prime mu, then you should get eta so a map which takes x to x prime and preserves this invariant interval is exactly what you call a Lorentz transformation. By the way, this equation can also be written in the form eta rho sigma is eta mu nu del x mu del x prime rho del x nu which should remind you of the transformation rule for a 0, 2 tensor, if you know what that is. For the time being, we will not really need to know that, but we have discussed tensors, etc. elsewhere. So, if you want, you can also look up those videos. Now, a coordinate transformation which takes x0, x1, x2, x3 into x prime 0, x prime 1, x prime 2, x prime 3, and which preserves the invariant interval can be shown to be linear. In fact, the most general form that you can write down for such a coordinate transformation is the following. X prime mu is lambda mu nu x nu plus a mu, where a0, a1, a2, a3 are constants and lambda mu nu form elements of a constant matrix. That's not enough. In order that this satisfy the invariance of the interval, you must actually have an additional property, which is simply this. Notice that if this is the transformation, dx prime mu is simply lambda mu nu dx nu, and so eta mu nu dx prime nu is given by eta mu nu lambda mu rho dx rho. Note that I have to actually change the notation a bit, or the index I can no longer call nu because I have another index nu here. And then you have lambda nu sigma dx sigma. So this is eta mu nu lambda mu rho lambda nu sigma dx rho dx sigma. But the invariance of the interval would insist that this particular quantity has to be the same as eta rho sigma dx rho dx sigma. So a quick comparison should tell you that we have this condition eta mu nu lambda mu rho lambda nu sigma equals eta rho sigma. Now, while this is a correct conclusion, and this is the property which the lambda matrix elements do obey, there is one important catch here which we have to bear in mind, which is the argument that because eta mu nu lambda mu rho lambda nu sigma contracted with dx rho dx sigma is the same as eta rho sigma contracted with dx rho dx sigma, these two things have to be equal, is really not quite perfect. Note that this actually implies that eta mu nu with lower indices, lambda mu rho lambda nu sigma minus eta rho sigma contracted with dx rho dx sigma gives you 0. That, of course, is exactly what you get when you subtract these two quantities. Now, this thing contracted with dx rho dx sigma gives you 0 does not necessarily imply that this thing is 0. Note that because dx rho dx sigma, this quantity is symmetric in the interchange of rho and sigma, if you took anything which is antisymmetric in the interchange of rho and sigma and contracted it with dx rho dx sigma, the result would be exactly the same if you were to change the indices. In particular, if you were to interchange the two indices. But this part is exactly the same as this part. And if A rho sigma is antisymmetric under the interchange of indices, then this part, these two are negatives of each other. Which means this expression, which is equal to this expression, also has to be negative of this expression. And that, of course, would imply that this is 0. So if A were antisymmetric in rho and sigma, contraction with dx rho dx sigma would give you 0. So the best you can say directly is that this quantity, which when contracted with dx rho dx sigma gives you 0, is actually something which is antisymmetric in rho and sigma. However, you can easily check using the fact that eta mu nu is symmetric in mu and nu interchange, that this quantity in the bracket actually happens to be symmetric in rho and sigma. Interchanging rho and sigma will not change the object. Just to demonstrate that, if you were to interchange rho and sigma here, you would end up with eta mu nu lambda mu sigma lambda nu rho minus eta sigma rho. Note that this quantity, of course, is the same as eta rho sigma. To see that this is exactly the same as this, all you have to do is use the fact that mu and nu can be interchanged, so that instead of eta mu nu, you can call this eta nu nu, and instead of this being called mu and this being called nu, you should call them nu and mu. And now you can easily see that this thing is the same as this, just written in a slightly different order. Of course, you have to use the fact that eta nu mu is the same as eta mu nu. So, because this quantity is already symmetric in the interchange of rho and sigma, we can conclude that this has to be equal to 0. Because as we have shown, the only possibility is that this is antisymmetric in rho and sigma. So, something which is both symmetric and antisymmetric in rho and sigma has to be 0. So, at least we have ended up with this property for the lambda matrix elements, which is a very important defining property. Now, we can write this in matrix language, and that often is convenient. If you say the matrix L has elements, mu nuth element given by lambda upper mu lower nu. So, this is just a definition of the matrix for us. Then, you should be able to check rather easily that this is the rho sigma element of L transpose, and that's why you have, instead of lambda rho mu, you have lambda mu rho here. That's why it's L transpose, eta L, and the matrix version of this equation is L transpose eta L equals eta. Now, an immediate consequence of this equation is, if you take the determinant of both sides, you get determinant of L transpose eta L equals determinant of eta. The determinant of L transpose eta L is determinant of L transpose times det eta times det L, and determinant of L transpose is same as determinant of L, and coupling all these together, you get determinant of L whole square equals 1. So, det L has to be plus or minus 1. So, the matrix that you make out of the Lorentz transformation coefficients actually happens to be either one with a plus 1 determinant or one with a minus 1 determinant. By the way, the transformation that we wrote down here, x prime mu equals lambda mu nu x mu plus a mu, is actually more general than the Lorentz transformation. In the Lorentz transformation, we assume that both inertial observers have the same space-time origin, that is 0, 0, 0, 0 maps onto 0, 0, 0, 0. That, of course, is a special case of this where a mu's vanish. So, you just have x prime mu equal to lambda mu nu x mu. The a mu's are, of course, nothing but translations of space-time coordinates. And so, this kind of transformation is actually a combination of Lorentz transformation of the coordinates given here, followed by a translation. And the formal name for such transformations is Poincaré transformations, named after Henri Poincaré, who was one of the last great polymaths in science and who has been credited with many things, including setting up the subject that we today call chaos, as well as being one of the forerunners of relativity theory. Somebody who many claim would have discovered relativity theory even if Einstein had not been in the picture. Now we have already seen that the determinant of the matrix formed by these lambda mu nu coefficients has to be either plus 1 or minus 1. Another very important property immediately follows from the relationship eta mu nu equals eta rho sigma lambda rho mu lambda sigma nu, the defining property for the Lorentz matrix elements. The property follows simply by putting in mu equal to nu equal to 0 in this expression. Eta 0, 0, remember, is minus 1 in our version. So what we have is eta rho sigma lambda rho 0 lambda sigma 0. Now note that eta rho sigma is itself diagonal, so there are only 4 non-zero terms here, corresponding to rho sigma equals 0, 0, 1, 1, 2, 2 and 3, 3. Just by putting in the values one after the other, the 0, 0 term of course has a minus 1 for eta 0, 0, and that's for rho equal to 0, sigma equal to 0. So this gives you minus lambda 0, 0 whole square. The other three terms come with a plus 1 coefficient because eta 1, 1, eta 2, 2, eta 3, 3 are each plus 1. And they give you lambda 1, 0 whole square plus lambda 2, 0 whole square plus lambda 3, 0 whole square. This whole thing is equal to minus 1, which means lambda 0, 0 whole square. If you take it to the other side, you get 1 plus sum over I going from 1 to 3 of lambda I 0 whole square, which means that this has to be bigger than or equal to 1. So an immediate consequence is lambda 0, 0. This coefficient either has to be greater than or equal to plus 1 or lambda 0, 0 has to be less than or equal to minus 1. Now, these two different properties, determinant of L is plus or minus 1 and lambda 0, 0 is either more than or equal to plus 1 or less than or equal to minus 1, actually plays a very important role in the theory of Lorentz transformations. We are going to discuss that soon, but before we do that, let us take a look at a few different ways in which we can write down the defining property of the matrix elements lambda mu rho. Well, we have already seen one of them, which is, of course, eta mu nu equals lambda mu rho, lambda nu sigma, eta rho sigma. And as we have said, this is exactly equivalent to L transpose eta L equals eta. This is the component version of that. This is the matrix version of this, of the same equation. It is easy to see that L transpose eta L equals eta can be rewritten in the form where L transpose is left on the left hand side and taking everything to the other side gives you eta L inverse eta inverse. What is going to be even more useful later is an expression for L transpose inverse which you get by inverting this, and that's eta L eta inverse. To see why this is pretty useful, let us try writing this expression in terms of components. So L transpose inverse is mu nueth element is going to be basically eta's mu rhoeth element, L's rho sigmaeth element, and eta inverse is sigma nueth element. Now this is eta mu rho. L rho sigma is our old friend lambda upper rho lower sigma. For eta inverse, we use a notation which is basically eta with upper indices. So eta upper sigma nu essentially is the sigma nueth element of eta inverse. By the way, our eta happens to be self-inverse, so eta inverse in this case is exactly the same set of numbers as eta, but this one actually talks about the inverse matrix. Now, we use a standard convention that the eta is used to lower indices. You contract with eta, the index gets lowered. So this rho index gets lowered and changed to mu. Whereas the upper index eta inverse actually, raises indices. So here the sigma index, which is contracted over, is actually raised and changed to nu. So this thing is what you would call lambda lower mu upper nu. For those of you who are familiar with covectors, this is exactly a covector transformation index. So L transpose inverse essentially is the way in which covectors transform and is written lambda lower mu upper mu. Now other properties or other ways of rewriting this expression which are pretty useful are as follows. One of them is you start with L transpose eta L and you can immediately equals eta, of course, and you can immediately rewrite this as eta, this eta in the middle, as L transpose inverse you're essentially taking this L transpose to the other side, eta, and also this L to the other side, L inverse. Now, if you wrote this in terms of components, you will get eta mu nu, the mu nuth element, is L transpose inverses mu rhoth element, eta rho sigma th element, followed by L inverses sigma nuth element. Note that L transpose inverses mu rhoth element is actually lambda lower mu upper rho. L inverses sigma nuth element is L transpose inverses nu sigma th element. So this is lambda nu sigma eta rho sigma. So this is exactly equivalent to the basic property that we wrote down before, but looks rather different in this form. Eta mu nu is lambda mu rho, lambda nu sigma, eta rho sigma. Now this actually has quite an important implication. Note that these are covector transformation coefficients, and eta having two such coefficients essentially means the following. If you were to treat eta as not just a bunch of numbers, but as a 0,2 tensor, what its index positioning actually implies, then the way it would transform under coordinate transformations is precisely this. It would pick up two covector factors, lambda lower mu upper rho, lambda lower nu upper sigma. Now what this expression shows is that this eta, which is a 0,2 tensor, is numerically invariant. Its components do not change under Lorentz transformations. It's the same for all inertial frames. That is why you have got eta mu nu back. Another useful equivalent version can be obtained just by taking this equation and inverting it. So you take this, invert it to get eta inverse is L, eta inverse L transpose. And if you now wrote it in components, you'll get eta, remember, upper mu, upper nu, that's eta inverse. L's mu rhoth element, that's lambda mu rho. Eta inverse here is eta upper rho upper sigma. Then you would have L transpose sigma nuth element, that's the same as L's nu sigma th element. And so this also says something about the tensor nature involved here. Eta rho sigma is like a 2,0 tensor, or what used to be called a contravariant second rank tensor. And the important thing is, if you treat this as a 2,0 tensor, the transformed value in any other coordinate is the same as the value in the original coordinate. So this is a numerically invariant 2,0 tensor.